Hey friends, so it is the first week of calculus and we get to talk about limits. So the problem at hand is we're given a graph of y equals f of x, and we need to find each of these things if the thing exists. So first things first, how do we read this? Right? This is read as the limit of f of x as x approaches 1. And what that wants us to do is say, let x get very close to 1, but not quite equal to 1, and see what the value, so the y value here, of f of x approaches. And we'll talk about what this means theoretically later, but for now, the very sort of casual understanding is the following. So let x approach 1. So we're imagining the x value is going to get closer and closer to 1 from both sides, but we're looking specifically at the values of f of x. So we really want to look along the graph. So as x approaches 1, from the left side I'm coming here, from the right side I'm coming here. And it looks like from both sides, my y value, the f of x value, is approaching the value of 1. Right? And I'm not scamming you, that is intended to be 1. So we'd say, okay, as x approaches 1, the value of f of x is also approaching the number 1. So we'd say this limit is equal 1. Very casual take on this for now. Just bear with me. So then we go, what happens as x approaches negative 2? So we want the limit of f of x as x approaches negative 2. So we go to the graph, and we want to approach negative 2 from both sides. So that will look like this. So notice something very interesting here. This is a hole in the graph, aka removable discontinuity. So f of negative 2 does not exist. So let me write that down. F of negative 2 does not exist. As in, there is no actual y value corresponding to an x value of negative 2. However, as x approaches negative 2, the y value approaches the location of this hole, which is the number 2, or intended to be 2, the way I've drawn this graph. So we would say, as x approaches the number negative 2, but x is not quite equal to negative 2, right? So we don't run into the does not exist issue. The y value for f of x is approaching the number 2. We would say this has a value of 2. Okay. Now continuing, as x approaches 4. So we look at it as x approaches 4. So along the graph, we're approaching here and here. So it looks like we're approaching this hole right here, aka removable discontinuity. But the value of f of x, so the y value is actually up here, and that's intended to be the number 2. So I would actually say that f of 4 is equal to, this is the value of the function when x is equal 4. But when we take a limit, we're not interested in what happens when x is equal 4. We're interested in what happens as x gets close to 4 but not quite equal 4. So it looks like the y value here is approaching 1. So we would say here, the value of this limit is 1. Now this seems a bit strange at this stage, right? Because we're distinguishing the value of f from the limit of f as x approaches a number. Just like we did here, right? The value of f does not exist, but there is a limit. Here the value of f is a different number than what the graph is approaching as a y value. So the limit does not match the value of the function. And these sorts of behaviors become super important when we talk about continuity later. Okay, but for now, we're just thinking about what the limit equals. Now let's look at the limit of f of x as x approaches 2. So I'm looking as x approaches 2. Now if I approach 2 from the left, I'm moving up the graph that way. Or if I approach 2 from the right, I'm moving down the graph that way. Okay. So this begs the question, what is the y value approaching as the x value approaches 2, but not equal to 2. Because keep in mind, there's a vertical asymptote here, so f of 2 does not exist. There is no y value associated with the x value of 2. But as a separate question, we're asking, is there any y value that my graph is approaching? And the answer is, I cannot give you a single number for y that my graph is approaching. Right? If I were to say, the graph is approaching 5, but it goes past 5 and keeps going. I could say the graph approaches 7 as a y value, but it goes past 7 and keeps going, because the vertical asymptote means my y value goes up indefinitely, forever. So there is no y value that I can declare that I'm approaching. The key is there has to be a single y value that I'm approaching. There isn't one. So I would say the limit does not exist. So here, the value of the function does not exist, and the limit also does not exist. Okay. Now let's take the limit of f of x as x approaches -1. So right here, if I approach from the left, I hit that closed circle, and if I approach from the right, I hit that open circle. Now, if I want to know the actual value of f of -1, now this is dictated by where the closed circle is. So that y value is supposed to be 3, so I would say f of -1 is equal to the value 3, but the limit. So if I approach from the left, it looks like my y value is approaching the number 3. But if I approach from the right, it looks like my y value is approaching 2. And I have to be able to declare a single number for the y that I'm approaching from both sides. And I can't. Because I'm approaching 3 when I come from the left, I'm approaching 2 when I come from the right. And that's not a single number. That's a, I guess, contradiction, conflict. So I would have to say that this limit does not exist, because I'm approaching a different y value from each side. Okay, so to quickly recap, right? If the graph is continuous, which we'll talk about a formal definition in a different video, but if the graph is connected, then the y value that I'm approaching is simply whatever the graph is. So in that case, the limit is 1. Even if there is a hole, aka a removable discontinuity, the limit is dictated by what the graph is approaching. So really the location of that hole. Right? We can see that here and we can see that here. Now if I have a vertical asymptote, then my y values go up or down indefinitely. So there's no single y value that I can say I'm approaching, hence the limit does not exist. And if I'm approaching a different y value from both sides, I also have to conclude that the limit doesn't exist, because I need a single value of y that I can claim the graph is approaching from both sides. Now, as a note before I move on, there will come a time later that we might talk about infinite limits, where if I say my y value is growing indefinitely, I might say that the limit is infinity, right? And that sort of on its face conflicts with the idea that the limit doesn't exist, although in this case, that's not a concern. Once again, we'll get to that at a future point. But I want you to know that at the beginning, before we introduce the concept of infinite limits, we have a strict, you need to have one declared y value that you're approaching from both sides to claim that a limit exists. And then later we'll expand on the idea of infinite limits. So a second problem that I think is worth discussing in the same video is this evaluate the limit. And so we're looking here, this expression is sort of taking the place of the f of x in the graph that we had previously. And our goal is to figure out what the y value is approaching as x gets very close to -8. So just to keep everything consistent, let's imagine what this graph would look like. So thinking way back to algebra and pre-calculus, we say, okay, I want to consider this f of x equals, and whenever I have sort of a rational function, so meaning I have a fraction with a numerator and denominator, with, I guess, x's in the numerator and denominator, I want to try to factor and see if I can gain insight, right? So we look at the top and we say, okay, well, there's an x squared in common, so I'm going to start factoring out an x squared. So x squared out of x to the fourth leaves an x squared, and then minus here, you factor out the x squared and you get that. The denominator is x plus 8. And then further, we look at that and go, oh, that's a difference of squares. We can factor that very cleanly. That's going to be x plus 8, x minus 8, because 8 times 8 is 64. So this is x plus 8 and x minus 8 all over x plus 8. And we see the x plus 8 factor in the numerator and denominator, and perhaps you remember that that shows up on the graph as a whole, which is also called a removable discontinuity for reasons that will become clear later. Okay, so the immediate question is, well, can we just cancel the x plus 8 on the top and bottom? Not quite, right? Because if x happens to be exactly equal to negative 8, then this becomes 0, this also becomes 0, and 0 divided by 0 is not a number, right? So we'd say that the value x equals negative 8 is not in the domain of f of x, right? So just specify this. We would say that f of negative 8 does not exist, okay? But every value of x that's not exactly negative 8, even if we get really close, like negative 7.99 or negative 8.00001, right? Not exactly negative 8. Then x plus 8 on the top and x plus 8 on the bottom will safely cancel, right? Because it's not 0 over 0, it's a number over a number, which neither number is 0. Okay. So we often will say, consider a lookalike function. So then we say, I guess this looks like, why don't we call this L of x, where we've eliminated this, we say it's x squared times x minus 8. Everywhere except x is exactly equal to negative 8, right? And so we can graph this sort of by the method of roots. We say, all right, well, where does this thing equal 0? Oh, it's when x equals 0 and where x equals 8. So I understand where x equals 0 and where x equals 8, I have the x-intercepts. And then I know because of the x squared, the behavior here is what we often call touch and turn. It does something like this. And we're going to end up in a situation like this. Now, this is very much not drawn to scale, so take this with a grain of salt. And then this extends down very, very far down. I am not being genuine with the shape of this. Here, we'll exaggerate. So it looks something like this, where when x is negative 8, I have a hole in the graph. Okay. So, thinking back to our previous example problem, if I want the limit of this thing, this expression, as x approaches negative 8, that's like saying I'm approaching x equals negative 8 from both the left and the right. I have to line this up to... So I promise I'm not scamming you. That is approaching x is negative 8. Okay. My y value is approaching the location of this hole, which means the value of this limit should be the y value corresponding to that hole. That's what we're trying to find. Okay. Now, the next question is, how do we find that? Because we often will teach students, when you take a limit, the first line of defense is to just take that value for x and plug it in to the expression. But we already know what happened when we tried to plug in negative 8 directly. We get 0 over 0. That's not a number. Okay. So I've had students come up to me and say, oh, 0 over 0 is not a number, so the limit doesn't exist, right? But you already know that's not right, because we looked at this graph, and our analysis was, as x approaches -8 from both sides, the graph is approaching a y value where that hole is located. There is a single y value that this expression is approaching. We need to find that. So the method is to think, well, this L of x represents this curve. Right? L of x has a value when x is -8. How come? Because L of x is after we've eliminated these factors of x plus 8. Right? So the f of x contains the fact that when you try to make x exactly -8, you get 0 over 0. Hence, f of -8 does not exist, and there's a hole. But the remaining behavior of this curve is governed by this lookalike function. So all we have to do is say, well, what is the lookalike function doing when x is -8? And we'll have an answer. Okay, that's sort of the idea. Now let's go through it algebraically. So we're going to say, okay, I'm going to factor this expression in the same way I did here, because that's going to let me identify where the hole is. Okay? So I'm going to say this is x squared times x plus 8 times x minus 8 all over x plus 8, just like we had before. Okay. Now, because we're in this limit context, we know that x is very close to -8, but it's not exactly -8, which means since x is not exactly -8, we get to cancel these things. So we're saying this is now the same thing as that. This is our lookalike function. And this is saying what happens as x gets very close to -8. The lookalike function doesn't have a hole. This is a continuous curve. So we're actually able to plug -8 directly into this lookalike function that's remaining and get a number that represents the location of this hole. So we can just do that. We can say, oh, this is -8 squared times -8 minus 8, which is -16. And quick maths, 64 times 16. Oh, that's 2 to the 10? Right? Because 2 to the 6 times 2 to the 4. So that's negative, because 1 negative, 1024. We have a number. Actually, I don't trust myself. Let's check. What did I say? It's -8 squared, so that's 64 times -16. We good. Okay. So, to recap what just happened, right? We said, hey, we'd like to take this limit, the limit of this expression as x approaches -8. Okay. Our first line of defense is to plug the number -8 directly in here, hoping that this expression sort of is a continuous function, and therefore we can just plug the number in and get a y value, right? That would be the same thing as if we said, hey, over here, this guy, what is the limit of this f of x? So we're going to go ahead and write the whole thing. So the limit of this expression as x approaches 8. Well, this graph is continuous right there. So I'm just able to say, hey, give me the y value when x is exactly equal to 8, which is 0 in this context, because from both sides, I'm just approaching the y value of 0. So if the graph is continuous at the point, you can just plug in whatever x is approaching and get an answer. That's the first line of defense. Plug in this value that x is approaching into the expression, see if you get a number. Now, in this case, we did not get a number because plugging in -8 gives you 0 over 0, which is not a number. Now, when you get specifically 0 over 0, you remember that that is a behavior indicative of a hole in the graph, which still means we can approach the location of the hole. So what we do next is we try to factor the expression we have to see if we can identify the location of the hole and say, because it's a limit, because x is not exactly that number, that allows us to safely cancel this and this because those are not exactly 0. They're close, but not exactly 0. Once we've canceled out those factors, we get what corresponds to the lookalike function, which governs where the graph passes through, rather I say where the graph is everywhere except for the hole, and also governs where the hole exists. I shouldn't use the word exists, I'm sorry. Where the hole appears, sure, that. And once you have that, you can say the lookalike function is continuous, so you can just plug that number in for the x's, and you get the value. So the answer here is negative 1024. So for the rant portion of this video, just some closing thoughts. First, I mentioned the word continuous at several places in the video without really explaining what I meant, and I try not to do that kind of thing too often, and I'm really sorry I did it. But continuity is going to be the topic of our next video, and I didn't want to use a different word and then switch it out with continuous later. So hopefully that will make more sense once we talk about continuity, and that you'll forgive me in the process. And I also alluded to a more theoretical definition of the limit rather than the casual one we're using. So specifically, when we write this and say the limit of f of x as x approaches c is this number, which we often write with a capital L, casually we say that pretend x is approaching the number c. Right? Very close to c, but x is not exactly c, and that's an important distinction. That in the process, the y values, the outputs of f of x, approach the number L. And we can look at a graph and understand that, and we can do a little bit of algebra and get some, good discussion there. And it turns out that casual definition is pretty much good enough for most of intro calculus, to the point where, a lot of calculus teachers and professors choose to leave it there and not talk about the, epsilon delta definition. Right? So I think of it akin to operating a car. Right? So when you drive a car, you don't really have to think about what's going on under the hood, right? You push one pedal and the car goes faster. You push the other pedal and the car slows down, and you sort of move your steering wheel and the car's body turns. Right? You don't have to think about the physics or the chemistry or the engineering that's really going on to make this car work. And a lot of times that's how we can approach calculus, where we can do a lot of the techniques and solve a lot of problems without ever coming back and thinking that hard about what a limit actually is, that our casual understanding of it really suffices. That being said, when I was an intro calculus student, my teacher did show us the formal definition of a finite limit, and it goes something like this, right? The limit of f of x as x approaches c is equal to the number L if and only if, for all values of epsilon greater than 0, there exists a delta greater than 0 such that, so long as the difference between x and the number x is approaching is less than this number delta, then the difference between the y values of f of x and this number L that we claim is the limit is less than epsilon. And this is the formal definition, right? And I say right very casually. We learned this in intro calculus, but we didn't use it to do anything. It was just sort of sitting there in the background, and I, acknowledged it. But I didn't start to use it for anything cool until I began studying real analysis, where we learn really how calculus is built from the foundation. And that was a great adventure in and of itself, but right up until that stage, I had done a lot of calculus without really doing anything with the formal definition of a limit. So I think I take the same approach as the sort of like math teachers I've referred to, where I like to keep it as the casual definition for now and say, hey, if you're going to study math, you want a career in math, you will deal with this later. For now, don't worry about it. And beyond that, and then the question is, what exactly is a limit used for? Like, why do we care about this thing? Why can't we just talk about when x equals c? And what is f of c? And so the immediate response is, well, we come up with new tools when we realize that our old tools are insufficient to describe the situation we're dealing with. So maybe a silly example is one that's just like what I showed in the, I guess, intro example, where, imagine I've got some function with a graph. Looks like this. Maybe there's a vertical asymptote here. And the graph looks like that, right? So this is the graph of y equals f of x. And let's just slap some values on here. Let's say this is, x is -2, this is x is a half, and this is x is 3, let's say. Okay. So because there's a removable discontinuity with like the hole there, f of -2 does not exist. Because of the vertical asymptote, f of 3 does not exist. So we have two cases where f of the x value doesn't exist. But we can see that they have different behaviors surrounding that place where f of the number does not exist. And so just saying D and E doesn't give us the full picture. We want more tools to describe this sort of like difference in behavior. And just like that, we look here and say, well, there's a closed circle there. So f of a half is that y value, right? We have a value for f. But there's this sort of jump discontinuity here. Once again, using a term that I'm not properly defining, right? But that behavior is not the same as sort of this behavior right here, where f of, let's just call this -1, f of -1 is that y value. F of 1/2 is that y value. But this behavior is different from that behavior. And so discussing limits gives us new tools to discuss different behaviors in the sort of surrounding areas, these neighborhoods of places where interesting things happen. So great, it's a tool. And it turns out that beyond that, this idea that x can get really close to a number without exactly equaling a number is really powerful. Like, let's imagine, what if we let x approach 0? Now we have a case where x is almost 0, but not exactly 0. So that means we can still take a difference between two things, because that difference might get really close to 0, but the difference isn't exactly 0. So there's still some interesting difference. So maybe that'll lead into a thing called a derivative. Or maybe we have things that are really small. They're almost 0, but not quite 0. So when we add them up, it's not 0, right? Because each individual thing is tiny, but not exactly 0. So a lot of tiny things put together might become something interesting. And maybe that leads to this idea of integration. Sort of differentiation and integration are the two pillars of intro to calculus. So I'm not giving a whole lot of, detail here. Forgive me. We'll get to that eventually. But in the meantime, I just want you to sort of believe me that a limit is one of those things that sort of sits in the background of calculus and allows us to do all kinds of cool stuff. And you don't have to engage with the formal definition or the theoretical underpinning at this time, but just trust me, it's really cool, and that is what it is. Well, thanks for tuning in, and I will see you all next time. Peace.